Hi, welcome back. We're up to lecture 16 here in Statistics 1. And in lecture 16, I'll cover repeated measures ANOVA. And this lecture is organized into two segments. And what I'd like to do is organize this by talking about the advantages or the benefits of repeated measures designs, and then talking about some of the risks or limitations. So first, the good news. Let's talk about the benefits. So segment 1, again, repeated measures ANOVA. Let's look at the benefits. There are obvious benefits to doing repeated measures designs, or what some people call within subjects designs. So just to be clear, those are the same. Some people say repeated measures, some people say within subjects. Same thing. And especially when it's hard to get access to subjects or cases, or if it's really expensive to do your experiment. So here at Princeton, we do a lot of neuroimaging experiments where we have subjects come to the psychology department, what will soon be the Princeton Neuroscience Institute. We will have them come and go into the scanner, and it costs a lot of money per hour to run that scanner, the MRI machine. So we almost always do repeated measures designs when we're using that scanner and when we're doing experiments using neuroimaging here at Princeton, because it's just so expensive. So that's the main benefit, is it's less cost. You need fewer subjects because every subject is exposed to every condition in your experiment. That also gives you more statistical power. And that's the really important concept to get out of this segment. That's the one new thing. We've already covered ANOVA, right? But you'll see the structure of the data is different. The F ratio is a little different. And that's the most important piece to understand. Those are the benefits. There are some risks and limitations. We'll talk about them in the next segment. So here's what a data structure commonly looks like when you set out to do a repeated measures ANOVA. It's sort of common in data management to have one row per case. In psychology, that's often subjects. So I have S1 for subject 1. That's a common organizational scheme, but you'll see that's not what we're going to do in R when we do a repeated measures ANOVA. Instead, and just to be clear, this is what I'm plotting here, or not plotting, but demonstrating here, are subjects in each row, and I'm using A again as notation for my independent variable. And let's assume that there are 4 levels of some independent variable A, and every subject is exposed to every condition. So subject 1 will give us 4 data points. That's a repeated measures design. The way to structure the data in R is a little different. R prefers to have the dependent variable in one column rather than across rows. So what's different is we have multiple rows for each subject. So subject 1, again, gives us 4 scores. So there'll be 4 rows for subject 1. Slight difference. Doesn't really matter, but you need to be aware of that if you're going to do this analysis in R. Okay, again, this is the most important concept to take away from this segment. Is remember in the between groups ANOVA, there were different subjects in each group. So the error was just the within groups variance. Why were people who were treated exactly the same in the experiment, why do they score differently on the dependent variable? We don't know. That's unsystematic variance that goes into our error term. If we have the same subjects in multiple conditions, then we can look for systematic subject variance. An example I use a lot in my classes here at Princeton is if we're doing cognitive psychology experiments, we often have people responding to things quickly on the computer screen, like the working memory tasks. Those stimuli were coming at subjects quickly. They have to respond quickly. Some subjects are just generally faster, and some are just generally slower. So if we're looking at reaction time across different conditions, if some subjects are just consistently slower across all the conditions, well, that's systematic. I can pull that out. So some subject variance can be accounted for in a repeated measures design, and it doesn't all go into the error term. That's a major advantage of this approach. So a way to conceptualize that is thinking in terms of and looking at Venn diagrams. So here's what I was saying about the between groups case, right? It was really easy. We had between groups variance and within groups variance. What I like to call systematic and unsystematic, or the good and the bad. Right? As experimenters, we want there to be variance as a function of our manipulation. Right? So we want there to be systematic variance or between groups variance. I've been using notation scheme A, sums of squares sub A. And the rest is just the within groups variance, that's the unsystematic. The F ratio is just mean squares A over mean squares S within A. That's it. It looks a little different now in the repeated measures case. We've still got our between groups variance, I should say between conditions variance, because we just take the mean for each condition, compare it to the grand mean, get the sums of squares that way. That doesn't change. But if you look down here, I can partial out any consistent subject variance and just ascribe that to subjects. So that's systematic. I can account for it. It's not error. It's not unsystematic. So what is the error term? And again, this is the really, really important concept to take away, is the error term is actually the interaction of the conditions A and subjects S. That may sound a little weird, so think about it this way. It's the inconsistency of subjects across conditions. If subjects are perfectly consistent across conditions, then that's systematic. There's no error. If subjects sort of change in random ways from one condition to another, not consistent with A, right, that's the definition of interaction, right? Then I don't know what's going on. That's error. So the F ratio now is mean squares sub A in the numerator, just like before, but now the error term is MS A by S, the interaction of conditions by subjects. That's a critical point to get, and one that even some of my grad students get tripped up on. So maybe review this slide a couple times. Make sure you know the difference between what the error term represents in a repeated measures ANOVA versus a between. Because what we're going to do in the next lecture is a mixed factorial where you have to deal with both of them at once. So you really have to have that concept down and be able to distinguish like what's the appropriate error term for the appropriate F test. Okay, so here's the mean squares and F ratios. This should all look familiar by now. We've got the F ratio down here, and mean squares, again, is always just sums of squares over degrees of freedom. At this stage, I'm not going to go through all the calculations for sums of squares. It's long, it's tedious, and you've seen it before. So I'm just going to cut to the chase. I'm going to give you an example, give you some data, and then just show you the mean squares calculations and the F calculations. And then I'll change the data slightly to show you how inconsistency of subjects across conditions contributes to error. So the example I chose to use here is a classic memory and learning paradigm in cognitive psychology called the AB-AC paired associate learning task. There's lots of variants of this, actually. They're designed to look at the effect of interference on memory. So we know that a lot of forgetting in memory just occurs to interference. And in this paradigm, what subjects do is they learn a list of paired associates, so just pairs of words that go together. And I'll just call that the AB list. And they learn them all to pretty high accuracy. Then they learn another list, the same list of words A, but now they have to pair them with new words, so I'll call that AC. Then their subsequent recall of B, if cued with A, is worse. There's interference, and that's called retroactive interference. It's a classic effect in cognitive psychology used to look at memory. So here's an example data structure. Again, I structured it this way just to make it, for ease of illustration. It would look a little different if we were doing this in R. So I've got my three conditions, A, B, A, C, A, B. Every subject was exposed to every condition. And what you see is I've got pretty high accuracy in AB, pretty high accuracy in AC, and then it drops down to about 75% in the second attempt to recall B after learning the AC pairs. You know, that's a classic retroactive interference effect. The question is 75 significantly different from 90, and is it significantly different from 85? We need to do a repeated measures ANOVA to know that. So again, I'm not going to go through all the sums of squares calculations because that takes a little bit of time. And we did it in the context of a one-way between groups ANOVA. And you'll have the values here, so if you want to try it yourself, you can do it, or you could actually plug that data structure right there into R and see if R replicates my handiwork here. I did write out the degrees of freedom because that's so easy. The degrees of freedom for A, there's 3 levels, so it's just 3 minus 1 or 2. We have to calculate degrees of freedom for subjects. I just put 6 in this example. We'd want more than that. But just for ease of illustration, I put in 6. So degrees of freedom sub S is 5. To get the interaction, you just take the product of those. So that's 10. And the total is the total number of conditions times the total number of subjects within each condition. That's little a times little n minus 1. And those all add up. Mean squares is just sums of squares over degrees of freedom. Again, I didn't show you the calculation of this, but just trust me. Sums of squares sub A is 700. Sums of squares A by S is 2.67. This gives us a ridiculously whopping F ratio. I don't think I've ever seen an F ratio that large in my own research. I purposely did that. Why is it so big? Let's go back and look at the data structure. If you notice, the scores tend to increase as you go down the rows, right? So there's a lot of consistency in the subjects. Subject 1 is just doing sort of worse overall, and subject 6 is just doing better overall. There's a lot of consistencies here. So all of that can be ascribed to subjects. And then there's a big effect of list learning. So there's not much unsystematic variance. If there's not much unsystematic variance, there's not much in that denominator in the F ratio. And that's why we got such a big effect. So let's change that. Let's play with the data a little bit and see how the F ratio changes. So all I've done here is within each condition, I just swap 2 scores. So if you go from one slide to the next, all I did was just swap 2 scores. This mixes it up a little bit. Now the subjects aren't quite as consistent across all the conditions. So now subject 1 is doing pretty well in list AB, and subject 6 is not doing as well. So we just flopped 2 scores in each condition. Notice that doesn't change the means at all, doesn't change the variance within a condition at all, right? But it will change the A by S, right? And that's reflected right here. So now we have larger variance that's just unsystematic. So sums of squares A by S is much larger. So we still have a pretty big F ratio, but it dropped dramatically just by swapping 2 scores in each condition. Again, the point of that illustration is to hopefully get you to wrap your head around what error is or what unsystematic variance is in the context of a repeated measures design. Again, this is a one-way ANOVA, so we're not done when we get to the F ratio because we have to figure out, well, what's the source of the significant effect? So you need to do post-hoc tests. And it doesn't work the same way in a repeated measures design as it did in a between groups design. Because remember, in the between groups design, we assumed homogeneity of variance. That is, we had different subjects in each group, And if we had homogeneity of variance, then we could just use that overall error term for any pairwise comparison. That's what Tukey's post hoc test does. But here again, remember the concept of error is different. It's A by S. So it depends on what levels of A you're looking at. You can't just use one overall error term for all your post hoc tests. So you need to calculate a new error term based on the conditions that you're comparing. And we'll do that in R. And the notation that I use for that is you just calculate a new F ratio, or you could just calculate a t-test, by taking out a subset of A. So that's what this symbol is denoting, just a subset of the levels of A. So I could just take the first two levels of A and compare those. Again, you want to correct for multiple comparisons. If we do lots of these, then we need to adjust our alpha. And since we're just sort of doing them on our own, like Tukey's test isn't doing it for us, we need to impose some sort of correction ourselves. And the most common approach to do that is called the Bonferroni correction. And all that does is it divides your alpha level by the number of contrasts that you're doing. So the more contrasts you're doing, the more restricted it gets. One more new idea here. I'll sort of zip through this quickly. This is a long segment. There's just one more assumption to take into account when you're doing a repeated measures design. We still have homogeneity of variance, but since we have the same subjects in each condition, we can also look at the homogeneity of correlation, or more technically, the homogeneity of covariance. So what this is saying is if I looked at the correlation between, say, the AB list and the AC list, I can look at a correlation, right, because it's the same subjects in each condition. I have these two columns. This is saying, well, that correlation should be about the same magnitude as the correlation between AB and AB at the end and AC and AB at the end. And we can test for that. The way to do that in R is to use Mauchly's test. There's another function. These are all made up for, named after the statisticians who created them. So just like we did Levine's test for homogeneity of variance, we'll do Mauchly's to test the sphericity assumption. And we'll get into this in R, but just for now, just note that if you do violate this assumption, most people just use these sort of built-in corrections, and these two were created by statisticians, Greenhouse-Geiser, and the other one, Winfelt. They just sort of adjust your p-values to sort of take into account the fact that you violated an assumption and you might be running the risk of increasing the probability of type 1 error. It's sort of the gist, glossing over it a little bit just for the sake of time.